An application that we're going to look at is fluid dynamics. So looking at objects in liquids and what are the forces and what can we learn from that. So we're going to spend a little bit of time looking at fluids. And when we're looking at fluids, it turns out to be more useful to talk about density than it does to talk about mass. When we're going to look at forces, we're going to consider not forces but pressure. But first, just a reminder, density, rho, the Greek letter, is mass over volume. So if you want to find the mass of some amount of liquid, you take the density times the volume. I want to give you a little bit of warning though. You're used to probably a density in grams per cubic meter. That's for water. In our MKS system, we want to be in kilograms, in cubic centimeters or milliliters, either one. But in MKS, meters, kilograms, this becomes 1,000 kilograms per meter cubed. Okay, so when you're used to 1 or 2 as your density, you're going to multiply it by 1,000 to get into the units we use in physics class. And that's just so we can use our acceleration due to gravity of 9.8 that we're used to using. Okay, so we talk about the density, and the reason we talk about density is the density is the same whether we have a small glass of water, a big water bottle, a pool full of water. If it's fresh water, it's all the same density, but the mass is very different. So density becomes a more useful way to describe what's going on. And as I said, to begin with, force, instead of force, it turns out to be more useful to talk about pressure. So this is P for pressure, not momentum. It doesn't have a vector, but it is the magnitude of the force over the area. So that's going to have a unit of Newton per meter squared, which is we call a Pascal. So you may be used to meters of, say, 1 atmosphere. And that's basically the pressure we experience most of the time because we're at sea level. That is equal to 1.01 times 10 to the 5th pascals. Okay, and again, this just keeps us in newtons per meter squared. So this keeps us in the MKS system. And the reason for using pressure is that if we have a container with liquid in it, then the pressure is always towards the outside, right? Liquid wants to flow and find its level, and so we have the pressure right here is pushing out against the side, and even if the side of the vessel is not straight up and down, but is sort of this kind of shape, right? If it's got the same amount of water, we still have pressure here, and the pressure really only depends on the depth in the material, in the liquid. So the pressure at some depth, which we're going to call a distance h, if we want to find it here, it's in all directions because liquid likes to fill space, if we think about that. So we can think about the pressure, which is force per area. We can draw, this is commonly done, we set up sort of this imaginary column of water here that's of height h, and we ask, what's the pressure right here? Okay, or in other words, what's the force per area? So if this has an area of A, okay, a surface area and a bottom area of A, then we can say that the pressure would be equal to the weight of this water in this column, so M times G over A, plus whatever the pressure is on the top, like the atmospheric pressure at the top. Okay, often it's going to be this value. So the pressure at the top we often call our P0, if you like. And so this would be mass times G over A. And to find the amount of that mass, we can write this in terms of density if we want. So mass is density times volume. So our pressure is equal to rho times V G over A plus this P0. So if we look at this, we've got volume. Well, what's the volume of this column? Well, the volume is the height times the area, right? The volume is whatever the area is. Maybe it's a circle, so it's a pi r squared, but it's area times height. And so if I put that into this equation, what this gives me is rho area times height divided by area times g plus P0. This is the pressure at the top, so maybe an atmosphere. And then this tells us how much the pressure increases as we go down in depth. So the pressure at any point in liquid pressure is whatever the atmospheric pressure is, plus what's called the gauge pressure oftentimes, rho GH, where H is our depth in the liquid. And those of you who scuba dive know, the amount your pressure increases every 10 meters or so down in the water. It's about an atmosphere every 10 meters. This has some immediate consequences. We can see some examples of where this is useful. So one is where we want to lift things. A hydraulic lift is something that's set up, I guess it's something like this. So it's a platform and a small platform, and it's connected with some kind of fluid in between these platforms that can move up and down. And the point of this is that if this is a liquid, then the pressure at this point, at this height, the pressure here is equal to the pressure at this point. And both of them have a pressure that's equal to the pressure at the top plus rho GH, the same thing we found before. So that says the pressure on this platform, P2, is equal to the pressure on that platform. Now pressure is force over area. So this is a small area and this is a big area. But if these are going to be equal to each other, then that means this is a small force over a big area and this is a big force over a big area. So what it means is you can apply a fairly small force here over a small area, and you can get then a fairly big force on this bigger area, as long as the fluid is what's called incompressible. In other words, we're not squeezing the fluid down as we move this down. Now, in order to lift something like this up, this has to travel much further, a huge distance, say, to move the same amount of volume. It might only move this tiny distance. But that's the way hydraulic lifts work, and that's what we use to, say, lift up cars or heavy machinery, right? We apply not a very big force here over a small area, which then lifts the car. And even your handheld jack sometimes is a hydraulic lift setup. You have to pump it a bunch of times to get the car to lift very much, but at least you don't have to be strong enough to lift a car on your own. So this is one application where we just say, hey, the consequence of the pressure being the same means the pressure here and the pressure here are going to be the same. Smaller area, small force, big area, big force available to then lift a car or something else.